Okay, this is a problem from the very end of the chapter, and it's a more difficult one. So the scenario is we have a hanging mass, but it's not just hanging, it's hanging from a pulley. So in other words, there's two ropes coming down and holding it. And then there is a sliding mass, M1, no friction is assumed, and we're asked to apply constraints to the problem here, and there are more difficult constraints here than we've seen previously to find what the um, acceleration downward for M2 and to the right for M1 is. So here on the left is a free body diagram for M1. There's a downward M1G and an upward N and a rightward T, and M1 is accelerating to the right, let us say with an acceleration of A. And here now is a free body diagram for M2. So M2 is acted on by two upward tension forces, one from each string. The tension force in the three string segments are all the same. We're using the massless string approximation here. So downward force of M2G and 2 T's upward. And so what we are going to conclude after some constraint equations is that the magnitude of A and the acceleration to the right of M1 and the acceleration downward of M2 are related by a factor of 2. The downward acceleration of M2 is half the rightward acceleration of M1. So in order to understand that, what I'm going to do is I'm going to use curvilinear coordinates, and I'm going to let U1 be the length of the string segment from M1 to the pulley, U2 be the second string segment length, and U3 be the third string segment length. And so clearly U1 plus U2 plus U3 is equal to L, which is equal to a constant, because the string is of constant length. And so therefore, if I take the time derivative of each one of these, remember the dot notation is what I sometimes use for time derivative. That's going to be 0 because the derivative of a constant is 0. And we also have U2 dot is equal to U3 dot. And that's true. Now if you look at the drawing I have here, if for example if M2 drops by 1 centimeter in 1 second, that means that U2 will drop by 1 centimeter in 1 second, and U3 will also drop by 1 centimeter in 1 second. And so that means that U2 dot is equal to U3 dot. That simple argument should convince you. So with these two expressions, the first one gives me U1 dot is equal to minus the quantity of U2 dot plus U3 dot, and then since the magnitude of these two is the same, I can just set both of these equal to U2 dot, and U1 dot is therefore equal to minus 2 U2 dot. So U2 dot is then equal to minus 1/2 U1 dot, and that shows that there is a factor of 2 between the two accelerations, this acceleration being half in magnitude of what that acceleration is. So I can then write a Newton number 2 in the x direction for M1, which is M1A equals T. And I can write a Newton number 2 expression for M2. Please note the coordinate system I'm using here. Just for a little change, I'm pointing y down, and there isn't an x direction for M2, so the y direction down is the key thing to pay attention to. And with y pointing down, then I bookkeep the signs in accordance with that. M2 times A over 2, that was the result of the constraint equation argument, is equal to M2G minus 2T. M2G minus 2T. So we can multiply this equation through by 2 and conclude that m2a is equal to 2m2g minus 4t, and then from the first number 2 equation for m1 I can substitute. I can get m2a is equal to 2m2g minus 4m1a. And so that allows me to solve for a, and what I get is a is proportional to g. The proportionality factor is 2m2 divided by the quantity of 4m1 plus m2. And so I can also calculate the tension in the string simply by multiplying this expression for A by m1 from our first equation here. So T is equal to 2m2m1 over 4m1 plus m2 times g. And to put some numbers in here, let's say that m1 was 1 kilogram, and that the hanging mass, m1 would be the sliding mass, m2, the hanging mass was 0.2 kgs, then the acceleration would be 2 times 0.2 kgs divided by 4 plus 0.2 kgs, which is 0.4 over 4.2 kgs times g. That turns out to be a little bit less than 10% of g. And roughly it's a little bit less than 1 meter per second. And then the tension gives me a little bit less than 1 Newton.